Hello, welcome to the Mighty Mighty Scoop Noodle Challenge. Let's begin the game, shall we? Okay, so here is the field, and let's see, this is you, and this is the other team. And over here is, let's see, there's a ball here, and there's a ball here, and there's a ball here, and there's a ball here. Okay? And right here there's a scoop, right here there's a scoop, right here there's a scoop, and right here there's a scoop, and there's also noodles here. And there's the noodles, there's the noodles. The noodles can float in water. Okay. Now, the object is to get the balls and the scoops and the noodles of the other team to the other side. The balls can be kicked over to the other side pretty easily. The noodles are really hard to throw. And the scoops, they can be thrown a decent distance. All right. And of course, it is legal to get everything by throwing it to the other side. However, in order to get to them, you have to cross a line and to the other team's territory, in which case the other team can tag you and you have to freeze and you have to sit down. They cannot tag you on your side. On your side, you can take them and they freeze. Okay? And that is the game. And whoever has all the other team's items on their side wins. Also, it's kind of neat because you do have to put the other team's items right here, and they can, of course, come here and steal them back. So it's this big war. Okay? Now, what does this have to do with my lecture series on the number E? I'll tell you. This game, Mighty Mighty Scoop Noodle Challenge, is a metaphor. The field is the space-time continuum. The other team represents the laws of physics. The scoops, your destiny. And I am your coach. Okay? The Mighty Mighty Scoop Noodle Challenge in this series represents some serious math problems, or mysteries, or conundrums, or just things to think about that I hope will guide you in this time of thinking, this time of learning. Okay? So, first, our first Mighty Mighty Scoop Noodle Challenge will be looking at rates of change. Very, very slow rates of change. Well, relatively. Okay? So, we're going to start with x squared. Okay? The squares that you know them are 4, 9, 16, 25, 36, and 49. And the differences between those squares, if we subtract 9, if we subtract 4 from 9, we get 5. If we subtract 16 from 9, we get 7. The difference between 16 and 25 is 9. The difference between 25 and 36 is 11. And the difference between 36 and 49 is, of course, 13. Okay? And let's do the difference again. The difference between 5 and 7 is 2. The difference between 7 and 9 is 2. The difference between 9 and 11 is 2. And the difference between 11 and 13 is 2. So, we've got it down to an arithmetic progression. Everything is a difference of 2. The rate of change is flat. It's constant here. Okay? Well, that's interesting, isn't it? Yes. Maybe not. Let's do the cubes, shall we? Okay. Bam. All right. What are our cubes? Our cubes are 8, 27, 64, 125, 216, 343, 512. And let's look at the rates of change, the differences between them. 27 minus 8 is 19. The difference between 27 and 64 is 37. And then we have 61, and 91, and 127, and 164. Okay? And then the difference between these are, let's say, 18, 24. The difference between 61 and 91 is 30. 36 between 127 and 91. 42. Okay. The difference between these two numbers, 6. These two numbers are 6. These two numbers are 6. These two numbers are 6. So when we bring our power up to 3, we have the difference of 6. The flat rate. When we were squaring it, they'd be 2. I wonder if a pattern's emerging. What would the pattern be? Let's do one more to the 4th power. Okay, everything's 4th power. What are our 4th powers? They are 16, 81, 256, 625, 1,296, and 2,401. Okay, what's the difference here? The difference between these two numbers, 65, 175, 369, 671, 1,105. Okay, and then let's see, the difference between these two numbers are 110, 194, 302, 434, 84, 108, 132. That's the difference between these, right? And finally, the difference between these two numbers, 24. And the difference between these two numbers are 24. And I assure you, if we keep going, it'll be a flat 24. So let's see. So the main point I want to make is that every time you bring the power up and you subtract the differences, and you subtract the differences of the differences, and the differences of the differences of the differences, you keep going, you're always going to get to a constant rate. Also, let's see, when the power was 2, and everything turned out to be, what did everything turn out to be? Everything turned out to be separated by 2, ultimately. When our power was 3, everything was separated by, eventually the constant rate we got to was 6. So 2 eventuates to the constant rate 2, 3 eventuates to the constant 6, 4 eventuates to the constant 24, right? So here's my question. What is the pattern here? And can you explain it? Right? My second question is, what if we go to exponentials? What will happen? And there's no huge, with this question, it's not hugely mathematical. It's just basically asking what's going on here. Because let's say we got 2 to the x, okay? Let's see, so we have 2, 4, 8, 16, 32, 64, okay? And if we take the differences between here, 2, 4, 8, 16, 32, okay, the differences here are 2, 4, 8, 16, it never goes to, it never ends, does it? No, it doesn't. What is going on there? That is my question. It seems that the rate of change does not change much. Well, does the same thing happen to 3? Well, not really, because if we do 3, 9, 27, 81, 243, what do we get? Well, the differences here, 6, 18, 54, 162, okay, and then here's 12, here is 36, here is 108, yeah, this 54 is not looking alive here, is it? 54. All right. What is going on there? Well, notice this is actually 3 times 2. And this is 9 times 2. Right? Okay. This is 27 times 2. Whoa. This is 3 times 4, or 2 squared. This is 9 times 4. Okay, 27 times 4. Okay. All right. So with 3's, or anything above 2, I would suggest, it's not exactly like that. Okay, what is going on there? Can we find a pattern? See, x squared, x3, x4, x5. If we find the differences between these, we get x times x minus 1. The difference is here, x squared times x minus 1. The differences between these two. The differences between these two is x3 times x minus 1. And the differences here is x4 times x minus 1. That's what's going on there. And if we do this again, what do we have? Well, we actually have, let's see, we have x squared minus x, right? And they're being multiplied by x minus 1. But this turns into x times x minus 1. So it's x minus 1 squared, right? Okay. And the differences between these two would be x squared times x minus 1 squared. And the differences between these, x cubed is x minus 1 squared. So, maybe I need to... So all of these just moves down, but they're all multiplied by x minus 1. And again, all these move down, but they're all multiplied by